So good morning to everybody. Good morning to everybody who's watching us online. I'm very honored to start our event here in IEA, Instituto de Estudos Avançados. The people who is behind this event is Professor Jerry Hogan, who is an emeritus professor of Toronto University in Department of Psychology, but unfortunately he couldn't come here due to a medical condition, and I have the honor and the difficult task to mediate this whole event. I'm Altair Lino de Souza. I'm a researcher at Unifesp, Federal University of Sao Paulo, and also a researcher in Center for Communication and Cognitive Science in NECA, USP. And I'm very happy to introduce our first speaker. Before that, how this event will work. We have two morning sections, two morning presentations, and then a break, and then we will return at 2. And from 2 to 3, we'll have a third presentation, and then we have 1 hour discussion. So for everybody who is watching here, and everybody who is watching us online, you can send questions. So if you can stay until afternoon, great, you can do questions. You can make questions in English, in Portuguese, we can translate, no problem at all. But if you are online, you can send questions too, and in the afternoon section, we will give these questions to our speakers. So our first speaker is Professor Johan Bolhuis. He has obtained his PhD in zoology at University of Groningen, Holland, and was a postdoc research fellow at University of Edinburgh, UK, and also in the Department of Zoology inside University of Cambridge. Nowadays, he is a full professor of behavioral biology at Utrecht University since 2001. He has served as an editor of Animal Behavior, and now he's the editor of Behavioral Processes Journal. Professor Bolhuis' main interests are in the behavioral, neural, and cognitive mechanisms of learning, memory, and development. In particular, the neural mechanisms of birdsong memory. And his talk to us now will be Twitter evolution, birdsong, speech, and language.
Okay, thank you very much. Obrigado, and bom dia, everyone. Thanks very much for inviting me. Also, thanks to Jerry Hogan. Unfortunately, he's not here. If you can see me, Jerry, hello, and get well soon. Yes, I'm going to talk about evolution. I hear some sounds, by the way. Some noise is coming out of this machine here. Okay. Anyway, so I'm going to talk about evolution and particularly about birdsong, speech, and language. And this very nice diagram that I'm starting with, if you look very closely on the top right, there's a little cloud in the shape of a human brain. So this is already an indication that maybe there is some kind of link between human speech and language and the songs of songbirds. And I hope to convince you that there is a link, and it's actually quite an interesting one. And it tells us a lot about the mechanisms and also about the evolution, the possible evolution of speech and language. Okay, so recently we published a number of papers, some linguists and myself, about the possible evolution of language. And it's led to quite a lot of discussion in the literature, you might say. And the reason for that discussion, is, I think, is manifold. It's not easy to analyze the evolution of language for a number of reasons. First of all, there is a problem of what is language. There are different opinions about what language actually is. What is the essential aspect of language? And for instance, some people might say, well, language is the same as communication, which I think is rather vague, but that's what some people think. So if you think that is the case, that language equals communication, of course, then you're looking at quite a different possible evolutionary scenario, because communication is occurring in all kinds of animals, in all animals, basically, and also, maybe also in plants. They communicate as well, but you wouldn't quite say that they have language. So there's a problem there if you have a different opinion about that. The other possible problem is that a lot of people, like Lieberman and many others, say that language is the same as speech. Speech equals language, and the other way around. And that's also another problem, because, for instance, what about sign language? Isn't that language as well? Of course it is. And so if you make speech the same as language, then you run into other problems, because other animals also have some kind of speech, some kind of vocalization, as we will see. And so you end up with a completely different scenario as well. Now, another view of language would be that differences that you can run into is that if you think of language as a cognitive system, as a computational system, as I think is a sensible way to think about it, that's quite a different thing from, for instance, usage-based views of language. That language is basically some kind of learning process. You start off with a blank slate, and then you, just by being exposed to language, you learn how language works somehow. And every individual apparently ends up with the same kind of language. And maybe a rather bizarre behaviorist kind of view, but a view that is quite popular these days. So if you have one of these views, that's also, you have a quite a different view of the possible evolution of that faculty, I think. So there's a lot of problems there, and there are also equally there are a lot of problems in the nature of evolution. How does evolution actually work? And there are misunderstandings about that as well. For instance, there's quite a lot of people these days, we call them evolutionary psychologists, that claim that evolution explains the mechanism. So if you want to understand the mechanisms of some trait, for instance, language or speech or whatever, you have to look at the evolution of it, because the evolution of that trait tells you how it actually works. I think it's a rather strange view, and I will try and explain why I think that is. But it is a view that is held by quite a lot of people. I would say that evolutionary analysis is basically a historical science. It's like you're trying to reconstruct the history of certain traits. How did these traits, for instance language or speech or anything else, how did these traits come about in the course of history, basically? That's what you're trying to do. And so those are quite different views on it. But if you do that kind of analysis, as I would advocate, then of course you run into problems immediately. For instance, in the case of language, there is, not everyone agrees with that, but there is, I think, no kind of human-like syntax in other species. So non-humans simply don't have the kind of language that we have. So that's a problem if you want to do comparative research. There's no other species that has that kind of language. Also, there's a question about how did evolution proceed? Are we dealing with some kind of common descent phenomenon that closely related species would have evolved similar mechanisms? Or are we dealing with evolutionary convergence that, for instance, the wings in bats and birds have evolved independently, and somehow they solved certain problems flying in similar ways, but independently of each other. So that could also be the case. Acceptation could be another possibility. And it's very difficult to find out which one is occurring, and maybe several are occurring at the same time. So that's quite a big problem, and I will go into that in some more detail later on. So what is language then? Well, as I say, it's not communication or something vague like that, but it's a computational cognitive mechanism. It's something in your head, in the head of an individual. There's something in your head called language. It's a computational system that has hierarchical syntactic structure at its core. It's not just some putting things together in some kind of associative learning thing, but it has hierarchical structure. And that yields an infinite array of structured expressions. So there's an enormous creative power in language that we can create sentences at will, and the interesting thing is that other people understand these sentences immediately, although they may never have heard them before. And importantly, I think this will come back later as well, that each expression is assigned an interpretation at two interfaces. Sorry. Here you are. So we have some kind of syntactic system at the top there, and the two interfaces that it sort of interacts with, that it is expressed at, is there's an external interface, so involving perception and production of, for instance, speech, but it could also be sign language or some kind of other modality. And there's an internal interface, the so-called conceptual intentional interface, roughly speaking, thought processes that it also has to interface with. And these are important distinctions, I think, that we'll come back to later on. Okay, now if you talk about language, speech, and birdsong, you might say, well, these are completely different entities. I mean, surely, if you look at the evolutionary tree, and this is a very simple version of the evolutionary tree, as you can see, and I'm taking into account various denominations here, being in Brazil, then if you look at the evolutionary tree, then it makes intuitive sense that if you would look at any kind of species, non-human species, that has anything like human speech or language, obviously you would have to be looking at our closest relatives, the chimpanzees, because the last common ancestor of chimpanzees and modern man was walking around on Earth about 5 to 6 million years ago, whereas the last common ancestor of modern man and the modern bird, like the zebrafinch here, was probably crawling around on Earth considerably longer ago, about 300 million years, give or take a few. So intuitively you were saying, well, if there's anything language-like in the animal kingdom, you would have to be looking at chimpanzees. But curiously, if you do that, and people have done that, of course, in great detail, then you don't really find sort of speech and language-like phenomena that I will go into in some detail in apes and monkeys. But you do find them in songbirds. For instance, songbirds, importantly, as you probably know, songbirds have to learn their songs from a tutor. So they're not born with a ready-made song in their head, but they have to learn it by being exposed to an adult individual of the same species. So there's some examples here. So these are sonograms, frequency of sound over time, of 2 songs of adult chaffinches. I don't know whether they live here, but they live in Europe a lot. And 2 songs of adult chaffinch males, and their respective sons are below them. And as you can see already, the songs of the sons are quite similar to those of the fathers. And it turns out it's not some kind of genetic heritability, but it's some kind of learning process going on. They have to be exposed to the songs of their fathers for quite a while to be able to copy it, to imitate it. So imitation learning is very important here, and of course something like that is going on in human infants. And human infants start to babble, start to talk. They try to emulate the sounds that the parents or other individuals make, and they're not so very good at it at the beginning, but they get better and better. So human infants are very good vocal imitators. Songbirds are excellent vocal imitators. Also certain marine mammals like dolphins and whales are good vocal imitators. But curiously, our closest relatives, as I just mentioned, apes, and also monkeys, they don't do that kind of thing. They don't show any vocal imitation. And maybe there was no need for them to do this. Maybe there was no need for them to evolve this ability. We don't know what happened. But it's a fact, I think, that they don't do it. So it's a very interesting discrepancy here, if you look at the evolutionary scale, if you like, that our closest relatives don't do this kind of thing that we do, which is quite an important cognitive ability, speech and language. But curiously, songbirds do that. So that's an interesting phenomenon, I think, to start off with. This is a cartoon that someone made when we published an essay in a popular journal some years ago where the ape or monkey doesn't have a clue what to do here, is asked to say apple, but doesn't know what's going on, whereas in this case the parrot, which is also a very good vocal imitator, not only can say apple if it had to, but it can also say something about particular kinds of apples, in this case Golden Delicious. Of course, it's not a Golden Delicious, it's a Granny Smith, but nevertheless he can do these kind of things. They're not perfect. Okay, so back to our simple evolutionary tree then. So the question arises, are we dealing with some kind of common descent phenomenon? So this orange asterisk there is the fact that we are most closely related to apes, or the other way around. Does that mean anything here? Well, it doesn't seem to mean much here in this case, in this particular trait. Of course, in other traits, it might mean something. So, for instance, birds can fly, and we and apes can't fly. So that's another where we are more similar to apes, perhaps. But on the other hand, if you look at vocal imitation learning, clearly apes don't do that, but songbirds do. So evolutionary convergence seems to be more important here. And I'll come back to this later on at the end of my talk. So if you look at how songbirds acquire their songs, how they learn their songs, it's quite an interesting phenomenon because the way they do it is very similar to how human infants start to acquire speech, basically. So they start off with a very simple kind of, you couldn't even call it a song. They start off with making funny, squeaky sounds. And I think I won't have time to go through the sounds here, but they make very funny sounds to begin with. Well, let me try it. Yes. So this is how young zebrafinch starts off. They're making funny, squeaky sounds. Then when it's a bit older, it makes a song. It produces a song that is very adult-like, but not quite yet adult, exactly adult-like. It's still scope for change, and eventually it ends up with a so-called crystallized song, where which is the song that, in this case, in this species, the animal has to do with for the rest of its life. So there are different phases in the acquisition of song. Just like in human infants. Of course, human infants start by babbling, also making funny squeaky sounds, and very gradually they arrive at producing proper words and proper sentences, perhaps. So there's an interesting similarity here. It could be completely coincidence, but it could also mean something. And there are other similarities as well, as you can see here. So there's this transitional phase called babbling in human infants and subsong in songbirds. And there is also a sensitive period. So in many species of songbirds, people have demonstrated that early in life it's much easier for these birds to learn a song than later in life. So the older they get, the more difficult it becomes to learn a song. And similarly in human infants, of course, as we all know, unfortunately, that the older we get, the more difficult it becomes to learn a new language with different sounds that we're not used to, that we have to acquire. And it's very difficult for us. So for me, it's very difficult to learn Portuguese, for instance. And for instance, for my daughter, when she was that age, as here on the photograph, she would probably learn Portuguese very easily, as she learned several other languages when she was young. But the older she gets, the more difficult it will become for her as well. So if she's watching, keep that in mind. So there are interesting behavioral similarities, and a few years ago, I and some colleagues of mine, we reviewed those similarities, first in a paper in another popular journal, and also in a book that Martin Everaert, a linguist in Utrecht, and I edited, and a lot of linguists and biologists contributed to it, where we discussed all the various similarities and the possible similar mechanisms. So there are behavioral similarities. I mentioned those already. There are neural similarities that I will discuss in some more detail. There are also genetic similarities that I will briefly discuss, and I think in the next talk we will hear more about that. I will say something about sleep, because that's also some more recent stuff that is actually quite interesting, also very similar. And then you might ask the question, well, given all those similarities, and I hope to convince you of those, are there also linguistic similarities? Do songbirds also have some kind of syntactic structure in their songs, the way that we have in language? Now, if you look at the neural similarities, so this is a very rough picture, because there's nothing like the real thing, but this, roughly speaking, if we talk about at the level of speech, so I'm not talking about language here, but the level of speech, roughly speaking, there is this kind of division of labor in the human brain. So this is a human brain, looked at it from the left-hand side, for obvious reasons that I will go into later. And there are two regions in the human brain that are particularly involved in speech. One region is in the frontal lobe, first described by Broca, French researcher. And he had lots of patients in his practice that had great difficulty speaking. So they didn't have problems understanding speech if you gave them certain tasks to do, but they had problems speaking. And invariably, post-mortem, he found that they had damage in a particular region in the frontal lobe, which is later called Broca's area. So that seemed to have something to do with the production of speech. There's another region in the temporal lobe, in the superior temporal lobe, now called Wernicke's area, because it was first described by Wernicke, who also had Broca's aphasic patients in his practice. But he had also other kinds of patients in his practice that could speak very well. They could produce very fine sentences, but they had great difficulty understanding speech. So they had difficulty processing speech, which if you gave them certain tasks to do, they were unable to do them properly. But they could tell you long stories about all kinds of things. So there seems to be a division of labor, then roughly speaking, I emphasize that once again, that basically there's a region, or a set of regions probably, a network, if you like, involved in production, mainly involved in production of speech. Again, I'm not talking about language, I'm just talking about speech here. And there's another region, more in the back of the brain, involved in the processing of speech. Okay. So, and as I said, in real life it's much more complicated. If you go a level up to real language, then there are different regions involved. There's whole networks that interact with each other. There are different connections between these networks that have different roles in syntactic analysis, in production, in semantic analysis, and all kinds of things. We discussed that briefly in another paper in TICS recently, but I haven't got time to go into that now, and it's also not so relevant now, I think. Okay, now if you go down to the bird brain, which doesn't have a very good press normally, but nevertheless it becomes more and more interesting the more you study it. So this is the brain schematically of a zebra finch, And roughly speaking, there are also two different networks in the songbird brain, and we reviewed that in two papers, and there's lots of other literature on it that's shown down there. There are two basic sets of brain regions that are involved in either the production of speech mainly, so those are those orange kind of blobs there, so they're involved in the production of song, so if you make small holes in them, they don't sing a song properly. And there are other regions, those yellow regions on the left-hand side, that are involved in the processing of song. So if the animals hear a song, any kind of song, and they don't sing themselves, then those orange regions will be inactive, but those yellow regions will be very, very active when they hear something, when they hear a song. Okay? So there's some kind of similar division of labor, perhaps, and whether it is similar to the human case, I will go into more detail at the moment. So what we set out to do some years ago was to see, well, what is the role of these different regions in song learning. And one idea that we had was that some of those yellow regions might be involved in the memory of song, the memory of tutor song. They have to store the information about the tutor song somewhere in the brain, and maybe that's one of those yellow regions. And so what we did was we did a number of experiments where we trained animals by exposing them. We reared animals by exposing them to a tutor, usually their father, so they could learn by imitation from their father. They could try and imitate the father's song. And there's variation between individuals. So some are better at imitating the song of the father than others. So there are good learners and poor learners. So here are some sonograms, frequency over time again. So the top one is the song of a tutor, so some adult zebrafinch male. The second one, the middle one, is a poor learner. So that one seems to have only copied two elements of the father's song, and the rest he just improvised apparently. And there is a third one, the bottom one, which seems to have copied rather a lot of the father's song. So almost all elements in its song were copied from the father. So there's variation, and we can make use of that variation. For instance, as we've done here. So this is the result of one experiment out of many where we looked at various brain regions. So on the right-hand side, HVC and area X, those are the sort of traditional song system nuclei that are active when the animal is producing song. On the left-hand side are two of those yellow regions that are active normally when the animal is processing song, when it's hearing song. And we looked here on the y-axis here is some kind of measure for neuronal activation. So we looked at the expression of immediate early genes, and I won't go into detail what they are, but they can be used as a marker for neuronal activation. So the higher the score on the y-axis, the more activation there is in neurons in the particular region. If you look on the right-hand side in both the song system nuclei, there's not much going on. I mean, there's something going on in HVC, but it's not related to, on the x-axis, the strength of song learning. So the more they've learned about the song, doesn't really matter about activation in the HVC. If you go to the left-hand side of the graph, there are two regions in the yellow, two of those yellow regions, CMM, there's something going on there, but most interestingly in the NCM, and I'm not going into detail what these abbreviations mean, but in the NCM, which is thought to be similar to auditory association cortex in mammals, including humans, according to some neuroanatomists, in that region there's something quite interesting going on that if you expose them again to the tutor song that they've hopefully learned to a greater or lesser extent on the x-axis, the more they've learned about the tutor song, the more activation there is in the NCM. So that's the first indication to us that maybe that region has something to do with the memory of the song. The more you've learned about it, the more that part of the brain is active. And this is just to show that it's not some kind of artifact of immediate early gene expression, because some people, of course, you always have critics say, well, you know, I want to see electrophysiology. I don't trust this gene stuff. Well, you can have electrophysiology on the bottom diagram. This is work done by David Vicario and his group at Rutgers, where they did electrophysiology of the NCM, that same brain region. And it doesn't really matter what measure they used here on the y-axis, but basically electrophysiological activity in the same brain region is also proportional to the strength of song learning. So whatever technique you use, basically, you get very similar results. So there's something going on in the NCM that has probably something to do with the memory for tutor song. Okay, so we end up with a much more complicated, so I've mirrored the brain now of the songbird. much more complicated picture. So the yellow blobs in this case are the song system ones, so they are active when the animal is singing. The green blobs here are active when the animal is hearing a song. And there's one particular region in those green blobs, the NCM, that's particularly interesting because the activation there is proportional to how much they've learned about the song. So it may have a memory function here. And if that's true, if the NCM does have a memory function and nothing to do with the production of song, for instance, if that hypothesis is true, then you would predict that if you make a small hole in that region, in the NCM, then you would get some kind of Wernicke-like phenomenon that you would impair perhaps the processing of a song because they can't access the memory of it. They wouldn't be able to recognize the tutor song perhaps, but you wouldn't do anything with the production of song because that's probably done by completely other regions in the yellow blobs. And this is exactly what we've done. Sharon Bolhuis, at that time a PhD student of mine, she's now at Wellesley College, and she made small lesions in the NCM and did some interesting behavioral experiments. So first of all, she measured the preference of these zebrafinch males before and after surgery, the preference for the tutor song over a novel song. So for some reason, these birds show preference to, they rather hear the tutor song than some unknown song, for whatever functional reason that we won't go into now. But they do that. So there's a very strong preference, as you can see in the left-hand diagrams. So these two groups are identical at that time. Before surgery, they have a very strong preference for the, anything above 50 is a preference for the tutor song, and they strongly prefer the tutor song. When you make a small lesion in the NCM, that's the yellow part of the graph, or you have a sham operation, the orange part of the graph, that makes a big difference. So if you make a lesion in the NCM, apparently they are impaired in the recognition of the tutor song. It's not completely wiped out, it's not completely random. So some people say, well, you should have made bigger lesions. Some of our American colleagues tend to say that. But nevertheless, there is a significant impairment. So they seem to be impaired in the recognition of the tutor song, which is more or less what we predicted. But these same animals, Sharon looked at the production of these animals after surgery and before surgery. And before surgery is the top one, and after surgery is the bottom one. And basically, they're exactly the same. So nothing happened at all whatsoever to the production of the tutor song, of the bird's own song. And of course, interestingly, they are impaired at recognizing the tutor song from which they have learned their own song. So they can produce their own song, but they're unable or they're impaired to recognize the tutor song from which they've learned their song. So a very interesting phenomenon, I think, and very, somewhat similar to, it's almost like we created some kind of miniature Wernicke patient that has no problem producing speech in the case of humans, but has problems in processing speech. So there's an interesting neural parallel there. Also, so I've talked about the sort of the green blobs, the sort of processing system. If you go back the other way, the other side of the system, the production system. For instance, HVC is one of those nuclei which has sort of a Broca-like function, if you like. We found, using the same technique of gene expression as a measure for neuronal activation, that this part of the brain, that's the middle diagram there, is activated in proportion to how much they've learned about the song when they're exposed to their own song. So when they're exposed to their own song that they produce, there's a lot of activation in the HVC, in the song system, proportional to how much they've learned about the song. You don't get that kind of correlation when they hear a novel song or when they hear the tutor song. So there seems to be a sort of dissociation here of, on the one hand, regions such as the NCM that are involved in the processing of song and in the memory of tutor song. And on the other hand, there are regions in the song system, which is activated when the animal sings, that maybe suggests that activation therein suggests that perhaps there is some kind of representation of the bird's own song there in those regions. Okay, so now the sound isn't working. Maybe you can put the sound back on. Sorry.
Nous parlons avec l'hémisphère gauche.
All right, this is Paul Broca saying we speak with the left hemisphere. Actually, it was me speaking, but this is apparently what he said once when he was still alive. We speak with the left hemisphere. We speak with the left hemisphere, sorry. And Wernicke could have said something similar, but then in German probably, that we not only speak with the left hemisphere, but we also process speech with the left hemisphere. Because invariably, the damage in those patients was in the left side of the brain. So there's an instinct, and as well, of course we all know that the particularly the left part of the brain is involved in speech and language in humans. And again, you switch the sound off, I think. All right, so this is the bird speaking, or actually it's my daughter speaking, but basically so what the bird was saying is that, we do the same thing. So this is a complicated graph. So the bottom one is adult animals, the top one is juvenile. Let's concentrate on the top one. And as you can see here, so this is gene expression as a measure of neuronal activation when the animal either hears nothing or the tutor song or a novel song. Yes. And as you can see in the HVC, in one of those production-related regions, there's quite a discrepancy between the left part of the brain and the right part of the brain. So there's much more going on, even if they hear nothing at all. There's much more activation going on in the left part of the HVC than in the right part of the HVC. So there's lateralization there. And if you look at the NCM on the left side of the diagram, the top, there's something quite interesting going on. If you expose them to a novel song or nothing at all, there's no difference between left and right. But if you expose them again to the tutor song for a short while, for half an hour, then suddenly there's a discrepancy between the left and the right part of the brain. That if they hear the tutor song again, and hopefully they recognize it, there's significantly more activation in the left part of the brain than in the right part of the brain. So in the NCM, there seems to be memory-dependent lateralization, left brain dominance. And that's a very interesting phenomenon, I think, because if you look at human infants, so these are 2-month-old human infants measured in France. Somehow they could keep their head still in the scanner. I don't know how they did that. Oops. How they did that, but anyway, they managed to do that, and you can see on the left-hand side there is, this is fMRI, there's activation in the left part of the brain, more or less in Wernicke's area, and on the right-hand side of the brain is in various parts of Wernicke's area there is activation going on, and the children are in the scanner and they can listen to a story being told either by their own mother or by another woman that they never heard before, but it's the same story. And as you can see here, there is significantly more activation measured in fMRI. The left part of the of Wernicke's area, when they hear the mother saying the story, compared to a unknown woman telling the story. And this only happens on the left-hand side of the brain, not on the right-hand side of the brain, and also not in other regions. So, interestingly, so we find also sort of memory-related lateralization, left brain dominance in infants. And also, if you go a step further, so if you here on the x-axis is the strength of song learning again, the solid line is the animals re-exposed to the tutor song, and on the y-axis is some kind of index of lateralization. So the more the score is above 0, the more there's left brain dominance, and if it's below 0, it's right brain dominance. And as you can see, the more they've learned about the song, the stronger the memory of the song probably, the more there is left brain dominance in these songbirds. And something similar is going on here, is going on in humans, human infants again, where when they are re-exposed to certain words in those stories, there's less activation when they hear the words that they've heard before, only in the left part of Wernicke's area, not in the right part of Wernicke's area. So again, there seems to be lateralization that is memory related. So again, a very interesting similarity between humans and songbirds. Okay, so that's as far as I go about the neural similarities. I want to say a few brief words about sleep, because recently it has been found that sleep seems to play an important role in learning and memory, not only in mammals, we know that for quite a while, but also in birds. And for instance, what people have found, Margoliath and his collaborators have found very interesting phenomena when they looked at electrophysiological activity in a particular part of the production-related regions in the songbird brain in RA. It's a motor region, basically. And I don't know whether you can see this, but you can see sonograms here of songs that they were singing during the day, and these birds, these zebra finches. And the top graph is bursting activity of neurons in the RA during singing. So there's a particular pattern of bursting of these neurons. Sorry. And interestingly, if the animals were allowed to go to sleep after the experiment, and the same measurements were done in RA during sleep, so the animals didn't sing, obviously, during sleep, they couldn't hear anything during sleep either. Nevertheless, there was activation activity in the RA. There was bursting activity of neurons in RA, which was actually very similar, not completely identical, but very, very similar to bursting activity during the day when they were singing that song. So they were not doing anything, they couldn't hear anything. Nevertheless, the activity in the brain, that part of the brain is very similar. So there may be some kind of activity going on during some kind of rehearsal or some kind of reactivation going on during sleep. So this is on the motor side of things. We ourselves found, more or less by accident, we found something very interesting in the NCM during sleep. So we allowed our animals to fall asleep as well, and then measured gene activation, gene expression, i.e. neuronal activation in the NCM, also in other regions. But this is the important one, because we found that there is spontaneous activation during sleep in this particular brain region, and the activation is proportional, again, to how much they've learned about the tutor song during the days earlier on. So they haven't heard the tutor song for quite a while, but when they fall asleep, there is activation in the NCM proportional to the spontaneous activation proportional to how much they've learned. So there's something going on in that part of the brain probably related to the learning of the tutor song. So in both cases, sleep seems to play a role, and of course we have to go into more detail. Well, what is the role of sleep then? Is it necessary to sleep after learning events to be able to learn properly? And that is actually what's going on in human infants. So again, there's an interesting parallel here. These are several papers about human infants learning artificial grammars, which they're very good at. But so they took infants into the lab and made them learn new unknown grammars to them. They're very good at that, but they were even better at it when they're allowed to take a nap in between different training sessions. So there again, sleeping seems to improve learning here. Okay, another interesting parallel. And more recently, another PhD student of mine, ex-PhD student, Sanne Moorman, she did her PhD earlier this year and actually got a cum laude. Now she's working at Boston University. She did an experiment where she sort of combined the lateralization theme with the sleep theme. So she reared zebrafinch males with their father, and at some stage the father was removed. They were exposed to either the sound of the song of their father or a novel song or nothing at all. And then they were allowed to fall asleep, and then activity was measured. And then interestingly, quite a complicated experiment, but if you look at, for instance, the bottom left, HVC, we see completely the reverse pattern that we saw early on during the day. So during the day, there is left brain dominance when they heard whether they heard the tutor song or nothing at all, there's left brain dominance. During sleep, there's right brain dominance in the HVC, completely reversed in that case. If you look at the NCM, of course, which is very interesting to us, there doesn't seem to be much going on, but if you look in more detail in the NCM, there is actually something going on during sleep, namely that there is lateralization in the NCM, but it depends on how much the animals have learned. So on the left-hand side in the top graph, you see the, what do you see? The poor learners? Yes, you see the poor learners. So they haven't actually copied many elements of the tutor song yet. And there you see right brain dominance. So the right part of the NCM is much more active than the left part of the NCM. But the animals on the right-hand side of the top graph, they have actually learned quite a lot about the tutor song. It's the other way around. They seem to be left brain dominant. And if you look at the bottom graph there, there's, again, the lateralization index on the y-axis and the strength of song learning on the x-axis. And as you can see, the more they've learned in any of the groups, whether they're exposed to something or not, the more they've learned about the tutor song, the more activation, the more lateralized activation, the more left brain dominant activation there is during sleep spontaneously. And interestingly, I haven't got the data to show you here, but actually Sanne scoured the literature on human speech and language, and she found too that there is a trend in quite a lot of the papers that when human infants or even adults learn a new language, the first language in case of human infants, initially there is either right brain dominance in Broca and Wernicke's regions to begin with, or it's the same on both sides. And the more they learn about the first language or the new language in case of adults, the more activation of those speech-related regions becomes left brain dominant. So again, there's a very interesting parallel going on here. Of course, this was measured in humans during wakefulness, And we don't know what's happening during sleep, but it would be interesting to look at these, for instance, at human infants during sleep, what's going on in the brain. Okay, so there's an interesting picture coming out of it. I think given the time, I will skip this because it's quite complicated, but we have developed some theory about what is going on there during sleep. But I will skip that for the moment. I will move on to, this is what I'm going to say about sleep. I'm going to move on to genes, and we'll probably hear more about that in the next talk. But as you may or may not know, there has been quite a lot of work done on the role of particular kinds of genes in speech, human speech. So there's a particular family in the United Kingdom known as the KE family. They're an interesting family because about half the members of the family have severe speech problems, so you can hardly hear what they're saying, I will demonstrate that in a moment. And this is the family tree, and as you can see, the dark blue members of the family, they have these speech problems, and about the other half of the family, they don't have any speech problem whatsoever. And it was found out by Simon Fischer and others that this particular gene, the FOXP2 gene, that is mutated in these members of the KE family. So there's an interesting relationship there. This gene seems to have something to do with it. And of course there's a whole discussion about what this gene does. And some people would say, we found a language gene, but Simon Fischer himself would be the first to say, yeah, that's complete rubbish, that this has nothing to do with language gene. But the relationship between genes and cognition is very, very complicated. You can't say that it's a language gene. It has something to do with certain aspects of language, maybe just speech, for instance. Okay, but that's the situation in humans. And interestingly, if you look at that FOXP2 gene, for instance, if you look at the amino acid sequence of the protein product of that gene, then the differences between species are quite small. So all species studied have a kind of FOXP2 gene that is actually very similar to the human version. So here you see different species, and the X's there are the differences in amino acids, just in individual amino acids between the two. So between humans and chimpanzees, there are only 2 amino acids are different in the protein. And between humans and mice, only 3, and between humans and zebrafinch, only 5. So minute differences, really. They're quite similar. So logically speaking, you would predict that, well, maybe this FOXP2 gene also has a similar role in, for instance, songbirds. And this is exactly what Constance Scharf and her collaborators in Berlin have done. So they knocked out the FOXP2 gene in zebrafinches, young zebrafinches, in a particular part of the brain. RA, if I'm not mistaken, yes. Oh, no, REX, sorry. So part of those yellow blobs in the production-related part of the brain, the song system. So they knocked out the gene in that particular part of the brain of young zebrafinch males, and they were impaired in their songs. So the songs, they weren't complete copies of the songs. There were bits missing, and the bits that they did copy were sort of incomplete. So there were problems with the song. So whether it's a learning impairment or whether it's a production impairment is not quite clear, I think. But there's some relationship. This gene seems to play some role in vocal production also in this species, interestingly. Okay, so as I already said, so FOXP2 is not a language gene, and Simon Fischer, as I said, is the first to say that. He's, most of his talks he spends 10 to 15 minutes explaining that it's not a language gene. And which is very good of him, I think. So, for instance, we should realize, of course, genes make proteins, not behavior. So there's not a one-on-one relationship between genes and particular kind of behavior. Also, FOXP2 is a transcription factor, basically, just like an immediate early gene is. So it affects the expression of other genes, and it could affect the expression of quite a lot of genes. So if you take out a key cog in the whole system like that, you might expect that lots of things are going wrong. And also, whatever effect it has, this gene, is probably in combination with lots of other genes, maybe hundreds or thousands of other genes, as usually is the case. Mutation of this gene has multiple effects, not only on speech. So, for instance, if you look at the brains of these, so these are MRI scans of the brains of the members of the KE family, and the yellow blobs here are differences between affected and non-affected members of the family. And then you can see that there are changes going on in the caudate nucleus, in the cerebellum, also in the inferior frontal gyrus, but in several parts of the brain there are fewer neurons in the affected members of the family than in the non-affected members of the family. So there's quite a lot of things are wrong, if you like, after this event. Maybe you can switch the sound back on.
Speech.
I'll just start this again.
Have a rare speech disorder.
So this is a member of the KE family.
Fox PH2. If you want to know more information about that, you can. Go to Google on the KE family.
Okay, so this is, this boy claims that he's a member of the KE family, and apparently he is, and he has, one of his hobbies is to make lots of YouTube movies, and this is one of them, and he has some kind of, blog or vlog or something, and, but if you listen to him, so he speaks with some difficulty, and it's subtitled in Dutch here, but he speaks, but actually what he says is grammatically quite correct, so he speaks proper English, it's just that he's not able to produce it properly, the way he would like to, probably. And interestingly, the next one, so if you can keep the sound on for the next one, so you will hear some quite awful music now. So I apologize for the bad taste in music here. So this is the same boy in one of his many YouTube movies where he's resynchronizing a particular song by Cliff Richard in this case, and he's doing the signing bit. And so I'm not an expert on signing, on sign language, but apparently he claims that he's doing some course in signing and he has some certificate already. It's a hobby of his, another hobby of his to do signing. And so apparently, he claims at least, I don't know, people should find that out, but whoever I asked, people have never looked at that, but apparently he can manage to speak sign language, apparently. So both, I think, his spoken language and his sign language doesn't seem to be much evidence for grammatical problems there. So grammatically, he seems to be spot on. It's just that the production, the vocal production is a problem here. So I think that's something to keep in mind. Okay, then we move on to the final question, the big one, if you like. So given all these parallels, given the parallels in behavioral parallels between birdsong and speech, given the neural parallels that we discussed in some details, given the genetic parallels, FOXP2, is there also a parallel at the level of, at the syntactic level? Is there some kind of syntactic structure in birdsong that is similar to the syntactic structure that is very important in human language, the essential part of it? And well, we've scanned all the relevant literature some years ago, Bob Berwick and some other colleagues of mine, myself, and Bob Berwick, of course, being a linguist at MIT, and basically we concluded that birdsong can be quite complex, like the song of this Bengalese finch here. It's quite a complex structure with particular patterns in it. But nevertheless, it doesn't have the same complexity as human language. It doesn't have the hierarchical syntactic pattern that is characteristic of human language syntax. So, so the answer is basically no. It's quite a different domain, really. It's not the same domain of complexity. And so we published that paper in TICS, but a year afterwards, there was an interesting paper in Nature Neuroscience, no less, and by two Japanese colleagues, who actually claimed that, quite the opposite, that actually songbirds do possess the spontaneous ability to discriminate syntactic rules. So a context-free grammar versus a finite state grammar, that they were actually quite good at discriminating that. And of course the grammar not being human speech, but Bengalese finch speech, as it were. And well, given the time, I won't go into great detail, but basically they had a very complicated experiment where they had patterns of Bengalese finch vocalizations put in a particular order. So they had a sort of some kind of grammatical order of embedded structures, sort of kind of context-free grammar versus a non-grammatical order. And what they did was they tested, so they exposed them to all kinds of different patterns, and then they tested afterwards, they probed whether they responded differently towards grammatical versus ungrammatical patterns of vocalizations, and lo and behold they did. So they responded differently to grammatical Bengalese Finch song than to ungrammatical Bengalese Finch song. So, you know, in Nature Neuroscience was raving about it, there was a News and Views and there was a big thing. But unfortunately, so we asked the authors, we were quite intrigued by this because, you know, if it's true it would be fascinating. It would save a lot of time if you apply for grants, I think. But unfortunately, it's not quite the case as they claim, because we, after some probing, we got the original data from the authors, and we reanalyzed the data, particularly Gabriel Beckers, who's in my lab in Utrecht. And he analyzed in great detail, and I won't bore you with the details, but he looked at the different strings that they used to probe the animal's behavior towards grammatical, what they call grammatical versus ungrammatical strings. And it turns out that the so-called grammatical strings were also the more familiar strings. So they were strings that they've heard quite a few times before, most part of it, whilst the ungrammatical strings usually were the unfamiliar strings. So basically what these people probably were testing was not grammaticality versus ungrammaticality, but it was familiarity versus unfamiliarity. And of course we all know that songbirds are very good at learning vocalizations and at recognizing vocalizations, so that's not such a big deal. So it's very likely that they solved this task simply by comparing familiar versus unfamiliar stimuli. So I think we can conclude there's no real evidence to conclude that they have this ability. So conclusion is that actually they don't, there's no evidence so far. They could do it still, but there's no evidence so far that they can actually do that. Unfortunately, you might say. So coming back then to the question I asked at the beginning of my talk, are we dealing with common descent or convergence, in this case of vocal imitation learning and vocal production? And I think the answer to that is both, surprisingly perhaps. So both are important. And I'll try to briefly try to explain that. So on the one hand, there is indeed homology. There are particular traits that are present in both humans and in songbirds, but also in mice and in apes and in monkeys. So we all have similar brain structures involved in vocal production, other brain structures involved in vocal process, in auditory processing and auditory memory. We also have similar genetic mechanisms. We all have the FOXP2 gene that is somehow involved in vocal production. Exactly how, we don't know yet, perhaps. So there is homology there. So common descent does seem to play a role in the sense that we all have the same common ancestor. Also, but on the other hand, there is convergence. So that what we do with it, what we do with the machinery that is there in all of us have that machinery available, the genetic and neural machinery, but it depends on the species, on the taxon, what you do with it. So we humans have evolved auditory vocal imitation learning, and songbirds have evolved something very similar, auditory vocal imitation learning. But somehow monkeys and apes and mice haven't done that. So convergence seems to play a role as well. But also what I said just now about syntactic structure, I think we also have to conclude that there is something there in humans that no other species seems to have, namely human language syntax. The hierarchical structure of human language doesn't seem to be, can't be found in any other species. So, for want of a better word, I call it specialization. And so maybe you can get the sound back.
Opan Chomsky style.
So yeah, this was a big hit a few years ago. So this is what we concluded. Even Chomsky took part in it. So this is what we concluded in a recent paper in Ticks. That we concluded that it may be. So we have to be very cautious, but it may be that the neural mechanisms that evolve from a common ancestor, i.e. the homology bit, so the fact that we have the same genes and brain structures, combined with the auditory vocal learning ability that evolved in both humans and songbirds, so this the convergence bit that it evolved not in mice and apes, for instance, contributed to somehow to the emergence of language uniquely in the human language lineage. So that's the specialization part. And on that note, I'd like to thank you for your attention and just show you some of the people that I collaborated with. Thanks very much. So I don't know how we're doing for time, but So we do the questions later? And then